All right, morning. Let's get started. Okay, we'll continue on the second order ODE, non-homogeneous. So when we solve non-homogeneous second order ODE, this table is basically the ultimate tool we use in order to get the solution. Because the solution to a non-homogeneous second order ODE with constant coefficient have two parts. One is YH, we call that, essentially the solution to the homogeneous one. And then we need a particular solution. And that particular solution will have a format from this table depending on the type of inputs at here. So I have given you a few examples already. But I want to go through a couple more, just to give you some more ideas of how do we use the table basically. So let's take a look at a couple more examples. Then we'll look at a different type of approach. So this one, y double prime minus 2y prime plus y equal to e to the power of t. Alright, so when you have this one here, we will basically step one to get the general solution for the homogeneous ODE. The characteristic is y squared minus 2 lambda plus 1 equal to 0. So this is the characteristic equation. The solution of this is lambda equal to 1. So in this case, you have two repeated real roots, right? And when you have two repeated real roots, the general solution for the homogeneous one, which we call the YH, is equal to C1 times e to the power of t, or lambda t, plus C2 times t e to the power of t. So that's your general solution for the homogeneous one. Step number 2 is to find this particular solution yp to the non-homogeneous. And this is where we'll look at the table now. So if you look at the table, this is the format of the input, and this is your choice of yp. Since your input is e to the power of t, so what we call is the basic choice of yp is equal to c times e to the power of t. That's your first initial choice of yp. So this is where you have to always be careful. You don't actually just stop here, because always bear in mind of the rules aside from the basic rule. So there's basic rule, there's also modification rule, and the summation rule. Summation rule is very distinct from basic rule, but the modification rule is a rule that you have to be extra careful here. How do we be careful? So you have your initial choice c times e to the power of t. You need to compare this initial choice with the basis of YH at here. So if you look at this and the two basic solution at here, apparently c to the power of e of t, what we call is it duplicates the c1 times e to the power of t. So it's nothing special. It's already included in the YH. Right? So your YP, the particular solution, is not really particular. It's part of this YH here. So then what do we do? So then we need YP to time a T. Okay. So time T to make it different from this C1 e to the power of T. That's modification rule. Okay. But then you have to be very careful here. You actually don't stop. You have to keep comparing. So you have to compare this, keep comparing with your YH head here. So you can see that this C times T e to the power of T again, it duplicates the C2 times T e to the power of T. So it further duplicates the second basic solution in the general solution YH. So now you have to keep modifying this YP to make it different, so times another T. So then you get CT squared e to the power T. Yes?
Would it be possible that you have to multiply the particular solution by T when you want?
Yes, absolutely. Yeah. This is the case when you have two repeated roots, right? You may have a case, for example, lambda 1 equal to 1, lambda 2 equal to 2, for example. Right? In that case, when you multiply T, it will not duplicate the other one, right? So you will basically stop there. Yeah. But this is the case you use the modification rule twice, right? To make sure your choice of YP is different from the two basic solutions in the YH. Okay, so that's a trick. Okay, so if there's such kind of question, right? So then the basically testing point would be: are you able to identify your choice YP, and did you compare your YP with your YH? Is that good? Okay. So the rest of the work are pretty similar. Okay, so then you calculate YP prime, YP double prime, and then you sub YP prime, and YP double prime into this the original equation here. Okay, and you solve for the C. So I leave that to you. So solve for C here. So you can practice yourself. There's a bit of a product rule here because this T squared times e to the power of T. So you can try it and find out what the T values is, or what the C values is. Okay, so that's product rule. Okay, so product rule is probably the modification rule. Okay, the modification rule could be the most confusing part. It's a matter how you modify it, under what condition that you should modify it. Right? That's the part you need to understand. Okay, so let's take a look at one more example. Okay, so to look at more of the summation rule. There's no T here for you. Alright, so if you have a second order differential equation and the input has a combination of exponential and sinusoidal input at here, and let's solve for this one. Okay, basically how do we find the particular solution? Okay. Again, step 1 is to get the general solution for the homogeneous one. Characteristic equation. Okay, lambda squared plus 2 lambda plus 5, and then lambda turned out to be a pair of complex conjugate roots. So -1 plus minus j2. Okay, so your alpha are equal to -1 and beta equal to 2. So your YH, okay, is e to the power negative t. This comes from the alpha, e to the power of alpha t, and then a times cosine 2t plus b times sine 2t. Okay. That's the general solution for homogeneous one. And the next, let's look at a particular solution, yp. Okay. So when you have a yp, you look at the type of inputs, right, on the left side, on the right side. Yeah. So you look at the inputs, there's exponential, there's also sinusoidal at here. Okay. So technically, if I go back to my table at here, when I have exponential, this is your type of yp. When you have a sinusoidal, okay, doesn't matter whether it's single cosine, single sine, or addition of sine and cosine, then your choice of yp will be this. Okay. So technically speaking, this is the part you use the summation rule. So you can consider you have two particular solutions. Right? You can have yp1, yp2. yp1 will be the one corresponding to the e to the power of 0.5t. yp2 will correspond to this term here. Okay? Yeah. So we can set up a yp1 according to the table. Let's call c times 0.5t. And then yp2, okay, is the term corresponding to this one here. So you can look at the table. The table will give you, okay, this expression. So yp2 will be n times cosine omega t. Omega here is 10, and m times sine 10t. So that's how you get the yp1, yp2, which are basically part of this particular solution. Now from here you have two choices, okay, and which is I'll show you. I want you to use a simpler one. The next objective to find c, m, and n, right? So this is what you need to find for this yp1, yp2. So to do this, you could basically put this yp1, yp2 together. Okay, so put them together, this plus this, and then you calculate yp prime, yp double prime, and then substitute back into the equation, compare coefficients, then get c, get n, get m. Okay, so that's definitely one approach at here. But because these two forms are distinctly different, right? Because one is exponential, one is sinusoidal. So what you want to do is, maybe simpler is, you do this. So obtain c first, okay, or separately. Obtain the c and m and n separately. By separately means you do this. So basically to obtain c, right, you calculate yp1 prime, yp1 double prime, and of course you still have your yp. So let me do a quick calculation here. Okay, so if I calculate yp prime, here's yp, so they get 0.5c of this. Yp double prime 0.25c times this. And then we sub this yp1 prime, yp1 double prime back into y double prime plus 2y prime plus 5y and equal to e to the power of 0.5t. Now you see the difference, right? So I'm not including that sinusoidal over here for my substitution. Okay, I'm only including this e to the power of 0.5t at here, because they're completely different form. Okay, you substitute here, you solve for the c. Okay, So your C can be solved, which is approximately, actually not approximate, I think it's going to be exact value, 0.16. Okay, so once you substitute here, right, back into this equation. So that's what we call separate. Okay, separating the steps to find C and Mn. So let's take a look at the M and N value. Now this one you need very careful attention to do the calculation, because it needs this sinusoidal here. Okay. Yeah. So YP2 is that expression. So we do YP2 prime first. Negative 10 times n sine 10t. So cosine derivative give you a sine, and then the 10 takes out to the front at here. 10m cosine 10t. Okay, so that's YP2 prime. YP2 double prime. Okay, so keep going. So 100n times cosine 10t plus 100 is negative 100m sine 10t. Okay, so YP double prime. And this time we're going to sub into y double prime plus 2y prime plus 5y equal to 40 cosine 10t minus 190 sine 10t. So this is separate. So we're not considering the exponential. We're only considering the m and n, which is part of the sinusoidal, right? So we only consider this one here. So it's like you're solving two separate, basically, first or second order ODE. Okay. Now this summation here is the part you have to be very careful with the sine, the cosine, and the negative and the positive. Okay? Yes.
I think you mentioned 190 sine t.
Where? Oh, did I? Sorry.
At the beginning of the expression.
At the beginning. Here? No. Up. Here? Oops. Over here?
No.
Up. Further up. Where? Over here?
Yeah. 190 sine.
Oh, there's a miss of 10t here. Exactly. Yeah. Yeah. If I got a sine t there, then I'm gonna further separate things. Eh? Yeah. Good points. Okay. Very good. So up to this, I think it should be all right, right? Up to this is all good. Okay. Sub this one over here, and sub this one over here, and of course sub the y over here. Okay. And group all the similar terms. Grouping all the similar terms, basically group all the cosine 10t term, group all the sine 10t term. Okay. So you get a whole bunch of coefficients and then cosine 10t, and then a whole bunch of coefficients and the sine 10t, and that equal to the right side. Okay, if you group all the terms. And then you compare coefficients. So whatever the coefficient for this cosine 10t on the left side should be the same as coefficient for the cosine 10t on the right side. So you'll get two equations. Okay, one equation is negative 100n plus 20m plus 5n equal to 40. And then negative 100m minus 20n plus 5m equal to negative 190. It looks like a three variable. It's not, still two variable here. Okay, you can further simplify. This is 100n plus negative plus positive, so negative 95n. So lots of big numbers here, but once you calculate, you find this one, for this one, n is 0 and m is 2. Okay, so that's actually pretty handy. Okay, so n equal to 0, m equal to 2, which means your yp2 is basically just 2 times, m is the coefficient for sine term, so it's 2 times sine 10t. So finally, you can put everything together, right? You get your y, general solution of y equal to yh plus yp1 plus yp2, and you get your whole general solution. Okay? Yeah. Now, some student asks, so what are we going to do with this A and B? Now, A and B can be calculated if you have initial conditions. Okay. So just the same way when you apply initial condition in your first order, in your homogeneous, your second order. Yeah. This one? Oh yeah, this, what do I call it, YP? This will be YH, exactly. Yeah, excellent. Yeah. All right, so I think I have covered a wide spread of different kind of examples. Okay, how do you make use of basically this table at here? Okay. This table, I believe, it will give you as a part of the formula in the final exam, so you don't have to worry too much. But you have to be able to apply this table and how to find the constants from the table. Okay. So that's the key. All right, so let's continue from here. Okay, so far up to this, this is the approach what we call the method of undetermined coefficients. In a simple term, we call it lucky guess approach. Okay. So we're guessing our particular solution through the table, okay, based on the type of inputs, right? But you probably already see the limits, right? The limitations of this approach. So the limitation of the approach is your input f of t has to be in an exponential form, right? And it has to be in a polynomial, and it has to be in a sinusoidal, or a combination of exponential and sinusoid. Okay. So your f of t, if the f of t is in this kind of format, perfect. You know, you can use the table, use this method on determined coefficient to solve for the particular solution yp. Okay. But what if f of t is not in that format? What if f of t is in a really strange function, right? F of t technically could take in any type of format. Right. So if that's the case, then you actually cannot use the method of undetermined coefficient anymore. Okay. So then we have to use the next approach, which is called variation of parameters. Okay. Variation parameters approach. Variation parameters approach is a very useful approach. Even now in this class, okay, even if you learn solving a linear partial differential equation in Hay transfer, okay, this is also approach to give you a solution. As a matter of fact, I think if you recall, okay, when we solve for homogeneous solution, if you recall that there's 3 different cases, right? First case is the 2 distinct roots, real roots. Second case is the repeated real roots. Okay, third case is the complex. In the second case, you remember in the second case when your lambda is repeated, let's say 1, right? When they repeated, so you can have e lambda t, right? You only have one basis. So what about the other one? We find the other one to be t times e to the power lambda t. Okay? And how do we find this? If we recall that we basically used the variation of parameter approach to find this one. Okay? So we multiply e to the power lambda t with a function c of t, and then we find c of t can be t. Okay? So that's variation approach. This is basically what we're going to do at here to apply this approach to the particular solution for the non-homogeneous one. Okay. So let me rewrite the type of function we're dealing with. Okay, so this is the one we're dealing with at here. First step, as usual, you need to find the general solution for the homogeneous one. Okay, so YH. So still have to find this one. Okay. It's the same type roots, the same approach. Second one, this is where things are different now. For the YP, okay, the particular solution, okay, we're gonna let our YP, okay, instead of picking YP from the table, we're gonna let YP, okay, to be M1 of t times Y1 of t plus M2 of t times Y2 of t. Okay. So if you look at the choice of YP, okay, it is a combination of Y1 and Y2, which are the two basic solutions, right? The two bases from your general solution for the homogeneous. But at the same time, we're multiplying each one, Y1 and Y2, with a function, M1 of t, M2 of t, not a constant, right? If I multiply constant, then there's no difference from YH. So we multiply a varying parameter. A function depends on the varying parameter t. Okay, one is M1, one is M2. Okay. So let's see where this will lead us to, right? Okay. So if we let a YP to this, we can calculate YP prime. Okay. So idea is just nothing missed on the top. So if we let this, we can calculate YP prime. YP prime can be calculated. There's basically a lot of product rule. There are two time function here. So M1 prime t times Y1 of t plus M1 of t times Y1 of t prime plus M2 prime of t Y2 of t and plus Y2, M2 and Y2 prime. Okay, so that's YP prime. Okay, two product rules for each term. So from here, okay, this is getting interesting. We're gonna impose, okay? I really don't want to keep so many terms. So we just go on out of limb. Let's impose a condition. And whether it's right or not, we'll see, right? Let's impose a condition. What do we want to do? We want to single out this one and this one. Okay? I'm going to impose that this term, these two terms, and make it 0. So we're going to impose this term to be 0. Now you might argue, why do you want to? What could you do that? Okay, so the means the ends justify the means. So you'll see that the way to do this actually works. Okay, but for now, right? So we are forcing these two terms to adding the summation of the two terms to be 0. Okay. So once we do this, then YP prime becomes just this term plus this term now, right? So M1 Y1 prime t plus M2, okay, Y2 prime t. Okay, so simpler, right? Getting rid of a few terms. Then we keep going. We will calculate YP double prime, right? The idea is essentially once we get YP prime, YP double prime, we put it back to the differential equation. We want to solve for those unknowns. Okay. Again, you need to apply product rule again to this term, right? So there are two terms here. Both are multiplication of two time functions. So M1 prime Y1 prime t plus M1 of t times Y1 double prime t. M2 prime Y2 prime plus M2 Y2 double prime. Okay, that's Y2 YP double prime. So this time we got everything. We sub this YP prime and YP double prime back into Y double prime plus AY plus BY equal to F of T. So we substitute back into this non-homogeneous second order ODE. And by the way, you're not going to do this every time when you solve this kind of question using various parameters. The way I'm doing this because I'm trying to derive the formula, and you will use the formula basically in the future. Okay. Once you substitute, so you basically substitute this term into here, and that term into here. Okay, and of course Y P into here. Okay. After you finish the substitution, and take out the common terms and do the substitution, you're gonna get basically the YP double prime plus AYP prime plus BYP. That's the substitution. This one equal to the following expression: M1T times Y1 double prime T plus Y1 double prime T, Y1 prime plus BY1. That's one term here. Another one is M2T Y2 double prime Y2 prime and BY2. And the last term is M1 prime T Y1 prime T plus M2 prime T Y2 prime T. And of course the whole thing equal to F of T. Okay, three big chunks. Three big chunks after you do the substitution. One over here, one over here, and then the last part is this. So what can we say from here, What can we further simplify this whole thing said here? Okay, so if you look at these results, look at the results carefully, especially the two red one, underline the red one, and look at the one in the bracket. The bracket is Y1 double prime A1Y prime plus BY1. What will be this term equal to? What's Y1? Y1, if you look at the Y1 and Y2, they are the two basis solution for the homogeneous one, Homogeneous means what? If you substitute Y1 over here, this one should equal to 0. Same thing for Y2. So basically you get this gone. You will only have the last two terms left. That's actually part of the beauty that we just imposed, the condition we imposed on, from the previous steps. So now we have very simple connection. So we have this one. For just a second here, let me insert a little bit space at here. So basically from here you get that expression. And don't forget the condition we imposed, which is what? The condition we imposed is this condition. That condition here. So let's put these two equations together. So that condition imposed is m1 prime t y1 of t and plus m2 prime t and y2 of t and equal to 0. So I'm putting these two equations together, okay, 1 and 2. And bear in mind what is unknown here. The unknown part is m1, m2, right? So we need to figure these two out. Okay. And now when I put this together here, as you probably can see, both equations have y1, y2, y1 prime t, y2 prime t. This is known, right? Because y1, y2 you can get it from the homogeneous one. And both equations have coefficient m1 prime, m2 prime, m1 prime, m2 prime. So this is where your linear algebra will come into you handy now. I can rewrite this equation, okay, this set of equation into a matrix format. The 2 by 2 matrix that here is y1, y2, y1 prime, and y2 prime. The column vector here is m1 prime, m2 prime, the coefficients. The right side is the 0 f of t. So remember this is known, okay? So you will be given, right, based on the function. And this will also be known based on your findings for y1 of t and y2 of t. So now you have, let's say, if I call this is a matrix A, this is a matrix V, this is a column vector V, and that's column vector B. So I can solve for V using matrix A inverse times B. Right? So this column here equal to the matrix inverse A times the column vector B. So let's do this. Let's see what's the inverse of the matrix A. If you recall that when you have a 2 by 2 matrix, okay, and you're interested to its inverse, now this is something I actually would encourage you to memorize for 2 by 2 matrix inverse. It's 1 over its determinant, right? So this is determinant AD minus BC. Then times another matrix, but you have to swap the D and A, and then add negative to B and C. Okay. So that you get the inverse of the matrix, 2 by 2 matrix. So in this case, A is this one here. So the A matrix, A inverse, should be 1 over the determinant of A, and then if I apply this formula here, I'm going to swap these two and add a negative to these two. So y2 prime, y1, negative y2, negative y1 prime. There. Okay. So what is the determinant for this matrix A? The determinant you can also calculate. You get y1t times y2 prime minus y2t y1 prime. Okay, that's a determinant, right? Determinant of this matrix. Okay. Incidentally, okay, this determinant, okay, is called the Wronskian. Okay. Sometimes we use WT to represent this one. It's called a Wronskian. I think I mentioned just a little bit about the Wronski when we talk about this. The concept was the linear independent and the linear dependent, right? So when you have two functions, y1, y2, how do I know whether they're dependent or independent? One approach is to form a matrix like this and look at the determinant matrix. If the determinant this matrix equal to 0, then the two function y1, y2 will be linear dependent. If the determinant is not 0, then they are linear independent. So if you look at this one here, in order to get a solution, absolutely I don't want my determinant to be 0. Right? If the determinant is 0, then I can't get a solution at all, right? So if you look at this one here, y1, y2, they are part of the homogeneous solution. So y1, y2 guaranteed to be linear independent. So this determinant is also guaranteed that it will not be 0. Okay. So if you in your calculation somehow you got a 0, right? So that probably will tell you there's somewhere something wrong with the calculation. Okay. Okay. So now once we get this, then I can summarize basically to get a solution. V is m1 prime t, m2 prime t, okay, and that equal to A inverse times B. Okay, and A inverse is 1 over the Wronski, which is the determinant. So we call this is the Wronski, right? So WT. Okay, and times y2 prime t minus y2t, y1 prime t, and then a negative here, and then y1 of t. Okay, that's A inverse times B. What's B? B is 0 f of t. Okay. Okay, this is your solution. But this solution is not for m1, m2. It's for m1 prime and m2 prime. So the derivative m1 and derivative m2. Okay. I will further simplify this a little bit because I need solution for m1 and m2. So m1 prime here, m2 prime here. So we can multiply this matrix out. So 2 by 2 times 2 by 1 should give you a 2 by 1. Okay. So that gives you 1 over WT at here. So you have that times this and this times this. So what do we get? Okay. We get y2 prime times 0, 0. Negative y2t times f of t. So negative y2t times f of t. Negative y1 prime times 0, 0. And then you have y1 of t times f of t. There. Okay. And if you carry out the computation for the right side, and you'll get this. So overall, you get your m prime, m1 prime equal to 1 over wt times negative y2t f of t, and m2 prime equal to 1 over the Wronski y1 of t f of t. Okay. So m1 prime is d over dt, right? So m1 prime, and m2 prime is dm over dt. So you multiply the dt to this side, okay, and then integrate both sides. So now we get our formula for m1 and m2 now. So m1 equal to integration. So top negative y2t f of t, bottom the Wronski dt. m2 integration, top y1 f of t, bottom Wronski dt. Okay, so after going through all of these steps here, truly when you solve, this is the two formulas that you will have to use. Okay. So those are the two formulas you will solve to get M1 and M2 of t. Okay? So let it thinking, right? Let it thinking into your mind. Just think about the process. My expectation is not for you to derive the two formula. It is to make use of the two formula to solve for the particular solution yp. Okay. I'll show you a couple examples in the next lecture. Okay. And then we'll go on from there. Okay. Any questions so far? Okay. Don't forget to go to your tutorial section this week for the quiz number 3.